Hello everyone, it's 6 p.m. I will wait for a couple of minutes and see if people join, otherwise, I will start after a few minutes. So it's 6:05. Let's wait for 2 to 3 minutes. Usually people join by this time, so that is why I'm waiting because in last 10 weeks, few people have joined like each time in the session. So that's why I'm waiting for a couple of more minutes. Okay, I think we can start. So let me use this one. Okay, if you can't hear me properly, then let me know. So there may be some background noise. The fan is also on. So if you can't hear me, then let me know. And also, I will try to adjust this in a way that it does not come, but it is easier for me if I keep this in side, because then I can check the chat box periodically. Okay. So let's start the session. Hello everyone, welcome to the live session for the course Sensors and Actuators. This is week 11, so we have only one more week left, and after that there will be the exam, whoever has applied for certification. And we have already covered so many topics, even though if you are, maybe you are not new to this live session, but I'll still give an introduction first. So I am Ananya. I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI, and I work here in Semiconductor Devices Lab Group. So let's start this session. So the first topic for this week is flexible MEMS. Okay. So what is MEMS? Micro electromechanical system. So it has just three parts. So micro, that means whatever the feature sizes will be. Feature sizes means the minimum feature dimension. Those will be in micron size and micrometer size. And electro and mechanical, it deals with electrical and mechanical properties like within one system. Okay. and flexible because we make the structure, make this MEM structures on a flexible substrate. Now what are some flexible substrate? So in this week we have discussed about PDMS. So there are other flexible substrates as well, for example polyimide. So certain flexible substrates can sustain relatively high temperature. Usually flexible substrates cannot sustain very high temperature. So if our system, like if we are designing something and the fabrication process involve very high temperature, then normally we cannot use flexible substrates. We have to modify our fabrication steps in a such a way that our substrate can handle those temperature. For example, we know that in normal APCVD or LPCVD, chemical vapor deposition techniques, the usually the process temperature is very high. Say we operate at 600,000 degrees Celsius, but most of the flexible substrates cannot sustain that temperature. So we have to modify our fabrication process in such a way that we will do the same deposition, say for example deposition of SiO2 or some other material, but with a deposition technique that requires lower temperature. For example, say PECVD. Okay, PECVD requires relatively less operating temperature compared to APCVD or LPCVD system. So that is why we prefer it for flexible substrates. And we have discussed about PECVD and how we can deposit SiO2 using PECVD in last week. Okay, so these are some points you have to keep in mind while working with flexible substrates, and while we are not only designing, but we will also eventually go for fabrication of the structures. Okay. Now why we are discussing MEM structures. So micro electromechanical systems can be used for many purposes. Why specifically we are discussing in this course, that is sensors and actuators. We are discussing this topic because we want to measure some electrical and mechanical properties within the same using the same sensor or sensing element in certain conditions. Okay. For example, last week we discussed about how we can measure tissue properties, electrical and mechanical properties of a tissue to identify some diseases like cancer. Okay. So what are those electrical properties and mechanical properties? Mechanical property was elasticity of the tissue, and electrical property was the impedance of the tissue. Normal tissue and a cancerous tissue will have different electrical and mechanical properties. Now the aim of MEMS sensor is that we want to measure both of these properties or different electrical and mechanical properties together. Okay. I will write it down. We use the system to measure electrical and mechanical properties together. Now if you are working in sensors, you already know that while while designing a sensor, we have to keep many things in mind. For example, what we are actually targeting, what is our target analyte, what we want to detect, and what is the range. Say if we are measuring some impedance value, then what is the expected range of impedance value. All these things we have to consider, and then we will design the sensor. So for that we will use some software like console to make the design of our sensor. Okay. After that we will go for fabrication. Now in this week, in first two classes, the fabrication of a MEMS sensor was discussed, so I will only discuss that part. So if I remember correctly, I think the sensor that was discussed, it was from Professor Pandya's group. So if you are interested, then you can search that paper and read more about it. We will focus mainly the fabrication of it, and the fabrication steps will be slightly different depending on the design of the sensor. But whatever was discussed in the lecture videos, I will only include that. And even if your design is little bit different, then many times the processes will be similar. Okay, we will use similar fabrication flow to make flexible MEMS sensor. Okay, maybe your substrate is different, maybe your design is different, but overall the different fabrication processes will be similar. So what was the sensor that was discussed? In the sensor, the flexible substrates that was used was PDMS. So initially everything was done on the surface of a silicon wafer for structural support, and after the whole fabrication process was done, the substrate was removed. So the silicon wafer was removed. So the substrate was mainly PDMS, that is the flexible substrate, and on top of that we have piezoresistive sensors. Those will measure the resistivity, so that will give us some resistance change depending on the pressure applied to it. That means it will measure the mechanical properties of our tissue if we are using it for tissue property measurement. That will measure the elasticity and other parameters, mechanical parameters of our tissue. So the strain, those piezoresistive sensors, so we have to connect it with some electrodes. So some gold electrodes were there. So that was our first layer or the first structure, and on top of that, to measure electrical properties, what we had, there was an insulating layer between, because we cannot directly make that electrode. So that was denoted as electrode 1 in the lecture video. I hope that you have gone through the video already. So after the insulating layer, the gold electrode was made, but it was not like the complete gold electrode. One SU8 pillar was there in between. So SU8 is normally used in MEMS systems because these are normally biocompatible and very hard, like it's a negative photoresist. After exposure it becomes very hard, and it gives good aspect ratio, and it is easier to use in MEMS systems. Okay, so that was the electrode 1, and that is how with that, using that electrode, we can measure the electrical properties of the tissue. So we had both mechanical way to measure mechanical and electrical properties. So how we can measure such type of a sensor? So I will write down the fabrication steps first, and we will go through it one by one. So fabrication steps are: first we will take the silicon wafer, and we will spin coat PDMS, which will be our flexible substrate. Okay, we have to cure it to get the PDMS layer. We have discussed about this technique earlier. Okay, so this is the first step, and after that we will make our gold electrodes. So these gold electrodes are to measure the change in resistance of our piezoresistive sensor. Okay, so we have to make our piezoresistive sensor next. So piezoresistive sensor is basically like a strain gauze. So the piezoresistive sensor that was discussed in the class was made of P dot PSS. So it's a conductive polymer. It shows piezoresistivity. Okay, that means the resistance changes due to the applied force or pressure. We are using this conductive polymer because ultimately we want to make a flexible device and a flexible sensor, so that is why we are using this kind of material. Okay. Now this design is specific, like they have made this design for a specific purpose, but if you want to make a different kind of sensor, then the materials that you will be using may be different. Okay, I'm just discussing what was discussed in the class. What is P dot PSS? So it's a conductive polymer. And it can be spin coated easily, and we can make the structure. Okay. Next is we will, so our piezoresistive sensor fabrication is done. Next we will make the electrodes. Of course we have to make the connections, but let's first focus on that, like how we can measure the electrical properties with different components of this sensor. Okay, next will be, we will make an insulating layer, SiO2 insulating layer, before making the electrodes. And we will use PECVD for that. As I mentioned that we are using a flexible substrate and we are using materials that cannot sustain very high temperature. That is why we will go for PECVD, which requires a relatively low operating temperature, around 200 degrees Celsius. After that, what we will do, we will make the gold contact pads for this sensor, piezoresistive sensor. Then we will make the other electrode, so that we for that we will first use SU8. We'll make SU8 pillar. So this SU8 is a negative photoresist, and we can make high aspect ratio structures using SU8, and often used in MEMS because this is biocompatible. Okay, we'll make SU8 pillars, and after that we will coat SU8 with gold to make the electrodes, because we want a metal for so that it will work as a electrode. Okay. And the last step will be remove PDMS from silicon substrate. So this is the fabrication flow. This is how we can make a MEMS sensor. Again, this design, this fabrication steps are specific to the design that was discussed. So this is one of his work. So I request you to go through the lecture video, and if possible go through the paper or the work that he has shared there, so that you get an understanding how the sensor actually works. We will mainly focus on the fabrication steps in today's class, in today's live session. Okay. So let's see how we can make the structure. Maybe I can use a different color. Okay. So first step will be, we will have this silicon substrate. We'll put PDMS, so this is PDMS. Okay. Next we will make this gold electrodes. How we can make this? So this is not only gold. For addition we will use chromium and gold. Okay, for addition we use chromium, a thin layer of chromium, and then gold. How we can make this gold electrodes, we have already discussed. This is by a technique called photolithography. So what we can do, we can follow two type of techniques. Like we can make we can evenly, like uniformly deposit gold on top of PDMS, and then we can do a photolithography, and after that we can do etching. That will remove the gold. So if we can do like photolithography process, and then after that we can do etching, and then we can remove the remaining photoresist layer. Okay, so this will be something like this. Suppose we have this PDMS and a gold layer on top of it, and then say we have photoresist here and photoresist here. Okay, we will do etching. So the portion of the gold that is below this photoresist will not get etched, because etching will be, say, directional. We are considering directional etching, say some physical technique. And after that, so our structure will be something like this. Gold will be here, there will be photoresist, and then gold and photoresist, and then we can remove this photoresist on using acetone very easily, and we will have this gold electrodes. Okay, after that what we will do, we will make the strain gauges. So for that we will use P.PSS. So we will evenly coat it. So it's a conductive polymer, so we can coat it very easily. So because this is a polymer, so this is our PDMS. Okay, this is gold electrodes. And then we will have our, so my drawing is not very good, but you can understand. Okay, so this is P.PSS. And now we want to make this piezoresistive sensor. So for that we will do another lithography. So this is like the second lithography. So how we can do the second lithography, the processes are same. We have discussed photolithography several times. If you still have any doubt, you can ask, but I will not go through the overall process again and again. So we will do photolithography, and that will give us the strain gauges for the piezoresistive sensors like this. So this is our silicon, this is silicon, this is PDMS. We will have our gold electrodes here, and we will have our strain gauges. So this is a cross section view. So this is chrome gold, and this is P.PSS. Okay. So this is our final structure after this third step. So we have already done our piezoresistive sensors, we have already made. So these will be used to measure the elasticity of a tissue, so the mechanical properties it can measure. And of course we have to remove it, the PDMS we have to peel off, because now it is on this rigid substrate, so we cannot measure the stiffness or elasticity of tissue like directly. Okay, the structure is not suspended, it cannot get bent. Okay, so we will ultimately remove this PDMS from silicon, but this is after the stick. Okay, let's see the next steps. Next, what we will do, we will make the electrode, but before that we will deposit the insulating layer to separate out the first layer and the second layer. So we already have what? We have silicon, we have PDMS, then we have these gold electrodes for the piezoresistive sensor. This is our piezoresistive sensor, which is of P.PSS. We will coat everything with a thick SiO2 layer. Okay, so this is SiO2 insulating layer. Okay. And on top of that, we will make, so how we can deposit SiO2, we will use PECVD. Next, we have to make the contact pads, because ultimately we want connection from this electrode. Okay, for that we will do another lithography to make the connections. Okay, for circuits we call it like vias, but it's MEMS sensor, so I'll not use that word. So we will do another lithography step. So we have already done the first litho, then the second litho, and now we are doing the third litho to make the gold contact pads. Okay, we will not go through the photolithography process. This was clearly discussed, like in detail it was discussed in the class. I will just give you the final figure. Okay. So how we will have, ultimately we will have a structure like this. So this is silicon. Everything we are doing on silicon, this is for structural support. PDMS, gold, and our piezoresistive sensor, and we will have the gold contact pads here. Okay, so this whole thing is gold. And another gold, so this is for our electrode, for electrode 1, that as I discussed in the class. So this is PDMS. So this is chrome gold. This is also gold. Okay. and this is pe.pss. Now you can see here that every time we will do lithography, so we will use etching also. For example, for this case we have to etch out this portion of SiO2. So after lithography, as I mentioned in very first few classes, that when we want to make pattern we have to do photolithography plus etching. Okay, it's not like patterning can be only done using photolithography, right? So in this case we will etch out SiO2 layer. So we know what is an etchant for SiO2 and what are the types of etching. Okay, so we can use buffered hydrofluoric acid for etching of SiO2. For silicon we will use KOH or other chemicals, and this is for chemical etching, that is wet etching. And if we want a very directional etching, that means we want very sharp side walls, in that case we will go for dry etching. And we have already discussed what are different dry etching techniques, like how we can do. So this is removing material physically by physically bombarding some ions and particles on the layer. Okay, this is how we can do. And we already know that etching, like in general, wet etching is very selective, because hydrofluoric acid will etch out SiO2, not some other material, whereas it will not give us a very good directionality, like the side walls will not be sharp. Whereas for dry etching we will get a very good side walls, but whereas it will not be very selective, it will etch away everything. Okay, if the material, if the energy of the atoms and ions are sufficient that it can remove the material, remove any layer, then it will remove. Okay, so it's not selective. So what is the best of both of this, like a combination of both of this technique, is reactive ion etching, where some chemistry is also involved, but it's a dry process, so it's like a physical etching kind of process. So we will do with using reactive ions. Okay, yeah, we have discussed about these topics earlier. I just reminded you, so it might be useful to, so that you brush up your knowledge for your exam. So this is our structure after the step. Gold contact pads. Now we will make the SU8 pillar and coat it with gold to make our electrode. Okay. So for that, what we will do, we will coat everything with SU8. Again, we can use spin coater, so it's a negative photoresist. We can usually spin coat it, and it's transparent, by the way. SU8 is transparent. And after the spin coating we will make the pillar. We will again do another lithography. Okay, and then we will remove SU8 with some physical technique. SU8 becomes very hard after exposure, so we will not go for etching because it's a polymer. We will just do exposure, and the portion where it gets, so it's a negative photoresist, so let me write it down here. So SU8 is a negative photoresist. Okay, so what happens in negative photoresist, becomes hard when exposed to UV. Okay, so we want our SU8 pillar here on top of this chrome gold layer, so we will do the exposure only here. That will make it hard, and the remaining portion will remain soft, and that we can easily remove using SU8 developer. Okay, so we use specific SU8 developer to remove unexposed region. So we will make SU8 pillar, and on top of that we will make this gold coating to make an electrode, because ultimately we want metal to make an electrode. Okay. So what will be our final structure? This is PDMS. This is our gold interdigitated electrodes, or not exactly interdigitated. As part of the design it was not exactly interdigitated. This is our contact pads. This is SiO2 insulating layer, gold. And then SU8 pillar, so maybe the height will be more compared to this gold thickness. Okay, otherwise we can just make a gold electrode directly. Okay. So I don't know the exact height or the thickness of this layers. I have not gone through the paper that professor mentioned in the lecture videos. If you are interested, then you can go through it. Usually this SU8 will be say 1 micron, or maybe a little bit more or less than that. So when we do spin coating, usually we try to keep it around 1 micron, 1.5 micron. Okay. So that will be relatively thicker compared to this gold. And then we will make a gold electrode here. Okay, so this is again gold. So this is SU8, this is gold. Now we have our this electrode to measure some electrical properties, and we have this contact pads and then this piezoresistive sensor to measure mechanical properties, and we will remove this silicon layer, silicon wafer, to make it a flexible substrate and flexible design, so that we can measure mechanical and electrical properties together. So our final device will be, final sensor will be PDMS. Electrodes, piezoresistive sensor, insulating layer in between, but we need contact pads for our sensor, and then we have another electrode to measure electrical properties. So this is our final device. Now remember, as I mentioned earlier, that this design is they have specifically made this design and fabricated this design for a particular purpose. Now this design can be different. What is more important, that you should know like what are the different fabrication steps involved. As you can see, like we have focused so much on photolithography in this course. You can see why, because so how many litho steps we need here. So here this is 1, this is 2, then this is 3 to make the contact pads, and after that to make the SU8 we don't do the whole litho, but we can consider it. So 4, and then again to make this gold electrode. So 5. So we need multiple steps of photolithography. This is like the heart of microfabrication, and we often do. And when we do multiple steps of lithography, then it is also important that we align our mask, align our features with the previous one. Say for example, we want our gold contact pads from here, not from here. So if we make our opening here, say to make the contact pads, then it will be on SU8, SiO2 and PDMS, so it will not make any contact, right? So alignment is very important, and photolithography is very important in any microfabrication or any fabrication of devices, especially when we are talking about MEMS devices, MEMS sensors, because the dimensions are in micron size, so we have to go for photolithography. You cannot rely on other techniques for patterning. So I will take a pause. If there is any question, you can ask. if not, let's go to the next topic. So when will be the exam for this course? Anyone was registered? No answer. I'll just check. Okay. Next topic was next video was on physical vapor deposition systems. We have already discussed. So there was this installation and operation of the system. Please go through it. I have not gone through it because we have like similar systems from HSV in our lab. So the processes are quite similar. So you can go through it, and I think there is not much to like explain about it. I'll just give you tell you some points, like I also discussed about these things last week also. In general, so these are true for any physical vapor deposition system. So what is physical vapor deposition? So PVD. So physical vapor depositions are the deposition techniques. We can make uniform film using these techniques, and these are physical, so no chemistry is involved, no chemical reaction is involved. What are the physical vapor deposition techniques? So we have thermal evaporation, thermal and E-beam evaporation, and sputtering. We had discussed about thermal and E-beam evaporation and sputtering in previous weeks. Okay, so I'll not go through it again. In any physical vapor deposition systems, what are the components we mostly have? We will have some vacuum pump, because generally these are done at like high vacuum condition or low pressure condition. Okay, there may be more than one vacuum pump, because we often do this deposition at a very low pressure, say 10 to the power minus 7 or minus 5 mbar, so which is very less, and we cannot directly use one pump to create that high vacuum. So we often use two pumps. We use one rotary pump to create low vacuum that can give us, say, pressure up to 10 to the power minus 3 mbar, and then from minus 3 to minus 7 to go for that, we will use another pump. It can be a turbo pump, it can be other type of pump, diffusion pump, that can create a very high vacuum. Okay, so we have a vacuum, and then we will have the main chamber. We might have a load lock chamber, because we don't want to want our main chamber to see the atmosphere directly, so we'll have another chamber where we will create some vacuum and then transfer our substrate and wafer to the main chamber, okay, without breaking the vacuum. We may have that, may not have that, depending on the system. And what other things we will have? We will need a water chiller, because we will create plasma, we will use electron beam and thermal, like resistive heating, so there will be a lot of heat. So we want our system to be safe, and there should be one cold water running continuously. So there will be some kind of pipe like structure along the main chamber, and water will continuously flow, and that will keep the main chamber cool. Okay, so we'll have a water chiller. We may have air pressure, air compressor. So if we have pneumatic valves, valve for operation, say we want to open or close something, either it can be a manual, we can do it manually, so there will be, say, one handle to move, open or close. Otherwise we will use air pressure to open or close something. For that we might need an air compressor along with our PVD system. Okay, but again, depending on the system, depending on the type of the system, we will have it, or sometimes we don't have. and then we will have the power supply and control unit. Okay, we if it says a RF sputtering, then we will have an RF source. If it's a DC sputtering, we'll have a DC source. And then if it is an EV evaporator, we will have some mechanism to create that electron beam and to move the electron beam to the proper spot, so that we can melt our material. We can melt our material without damaging the crucible. So what it will be, like, we will have a crucible usually of graphite, and we will have our metal here. Okay, and then we will try to put the electron beam at the center of the metal, not on crucible, because ultimately this electron beam, we want this to hit the metal or the target material that we are using, and then melt the target material, not the crucible. Okay, so we will try to move this electron beam at the center, and then it will move in this zigzag kind of direction inside this crucible, inside this near this material. Okay, near the target material. So for that we need some mechanism to control that. Okay, all these things will be there in the system. And what other things? I think these are the main components. There will be one main chamber, there will be pump, and we will have power supply and control unit, how we can control our deposition. Okay. And then we have already discussed about what are the safety precautions we have to follow while using a physical vapor deposition system. Main safety, it comes from, because it involves a vacuum pump, so we have to vent it carefully. So if our main chamber is at very high vacuum or low pressure, we don't directly open it. First of all, we cannot directly open it. The pressure difference will not allow us to open it directly. So what we will do, we will introduce nitrogen or some gas very slowly, so that it fills the chamber, and then we try to open it slowly. Okay, so these are the things we have to keep in mind. And say we are operating a e-beam evaporation system, then electron beam, when it hits the target material, and this target material when melts, then it glows, it glows very brightly. Okay, we should not see it directly without using any safety goggles. Okay, this is also very important while using this. And when we will load the sample, when we will load our target material, then of course we have to use gloves and other safety precautions that we normally maintain inside a clean room. Okay, and there may be some leakage in our system, so we have to keep an eye for that. Say usually our system goes to say 10 to the power minus 5 millibar pressure within say few hours, say 3-4 hours. And say you are doing deposition, and you can see that even after few hours it is not reaching to that level of vacuum, then there may be some leakage. Okay, if the leakage is large, if it's a very big leakage, then it will not even reach to -3 or something. Okay, so we have to check for it periodically. And since we sometimes use some reactive gases along with it also, okay, especially in sputtering, so there may be that leakage can be dangerous if we are using some gases, those are toxic. Okay, these are the things we have to keep in mind while operating a physical vapor deposition system. Next topic was 3D printing. So again, the videos that shows how we can make a design using a CAD software. So what is CAD? It's computer aided design, right? CAD is like not only we use this, we electronics engineer use different CAD tools, and mechanical and civil people also use. We can make the use of the CAD tools to make our design, and then using 3D printing technology we can print it. So you can make a variety of design using 3D printing technology and with different materials. So the ink that is used for 3D printing, so if we want to make some structure using certain material, first thing will be we have to make the ink. Okay, now if we want to make some structure using the available ink that is there with the 3D printer, then we can simply make our design using some CAD tool. The example that was shown was using Autodesk Inventor. Okay, so we can make a design using this tool and then use 3D printer to realize this design physically. Okay, so that's a 3D printing is a very powerful tool. People are using it to make different complex structure. So these are some advantages of 3D printing technology. I have never used this software. Okay, you can try it by yourself. The two videos that was on the software are like pretty self-explanatory. You will be able to use the software while after going through those videos. Okay, so these were the topics those I covered in this week. So I'll take a pause. You can ask if there is any question. Otherwise, I will go to the questions for this week. So no question, then we can go to the questions. So the first question is, I will write it down first. What is the primary function of PDMS in a flexible MEMS sensor? Like consider the example that we have discussed. We can use PDMS for multiple purposes, but consider the example that we have just discussed. Option A is conductive polymer, structural and flexible substrates, C is insulating layer, D is adhesion. So it's a very simple question, all of you can answer. Tell me the answer in the chat box. Answer is B. What about others? So There are only four people in the mid, so I expect answer from everyone at least. B. So in this case, we are using PDMS as a substrate.
Answer is B.
Yes, thank you. So in this case, we are using PDMS as a flexible substrates. Now, we have already discussed about PDMS molding earlier. Also, we can make like channels using this material, and PDMS is like I'm not sure about very thick, but mostly transparent acetylene layer. So it is useful in that way also, and many times this is used in biosensors, because as I mentioned earlier also, that when we are designing a biosensor, first thing we have to remember is that the materials we are going to be used should be biocompatible, and the second thing we should remember is that the accuracy and precision of the sensor should be very very high, because we are dealing with some say disease or other health concerns, right? So accuracy and precision is important, and biocompatibility is important. But for the example that we have discussed, this used we have used PDMS in this case as a structural and flexible substrate. Okay. Let's go to the next question. Complete the statement. Actuate is a negative photoresist used to create dash during MEMS sensor fabrication. Option A is contact pads, B structural pillars, C conductive layers. So what is the answer? Again, I will wait for some time so that you can tell me the answer.
It is structural pillar.
It's a
B.
structural pillar, B. Okay. So it's a negative photoresist. And why we use SU8, like particularly contact pads? No, SU8 is used as a structural pillar. So correct answer is B. Contact pads, the example that we have discussed, contact pads are made using gold, chrome gold, right? The answer is B. Structural pillars. So you can look what is SU8 in Google and find some information about it. So it's a very interesting material. We often need to use it as a negative photoresist. And so one thing I note, like as I mentioned earlier, and I have noticed that during in my lab also when I was working using SU8, so it becomes very hard. Okay, due to the exposure. It is very difficult to remove SU8, and we have to use like certain material, certain chemical for that. So it is very good for structural support to create different structures, and it is transparent. SU8 is transparent. It's a very liquidy consistency. We can easily spin coat it and control the thickness of SU8 depending on the like speed of rotation and duration. We can do that, and because it becomes very hard, and we can get a very good structural like support, or the good aspect ratio. What is aspect ratio? So when we make pillars, so say this is a vertical pillar, so this is this weight and this is this length. So the aspect ratio is L by W or W by L, whatever. So we can make like a very tall pillars with say less width, using some material. So SU8 is one material, and when we want to make this kind of a structure, we can use this material. And why it is important? When we want a very good high aspect ratio structure, sometimes what may happen, so this pillar, so you say you have like consecutive pillars, sometimes this one may topple on top of another. Okay, those pillars will not be exactly will not stand vertically. It may like bend a little bit. Okay, in certain cases we don't want that. So using SU8 we can make this kind of structure very easily, and that is why we use. And of course it is transparent, that is another advantage, and it's biocompatible as well. So SU8 is a thick epoxy based negative photoresist used to fabricate high aspect ratio pillars and microstructures. The next question. So again I will give some statements and fill in the blanks. During photolithography, a dash photoresist becomes more soluble in developer when exposed to UV light. So I'll not give you options, so it's a very easy question. You can tell me the answer.
Ma'am, positive photoresist. Positive photoresist.
Positive photoresist. Yes. So I expect answer from everyone. So these are polymers, positive and negative polymers, photoresistant polymer. So depending, so you know that in polymers there will be chains, right? Okay, carbon chain and the other material, okay, other component. So with exposure what happens, either they change grow, that is what happened in case of positive photoresist, and in case of negative photoresist there will be cross linking, so the chains will become like the bonding will become more strong, so they will cross link with each other. That's how negative photoresist become hard. Okay. So if you are interested, you can also look for what are the some examples of positive photoresist and negative photoresist. One we already know, negative photoresist is SU8. Positive photoresist, there are few, like can give you some example like ARP 53205350. These are some positive photoresist. Next statement is in photolithography, using a dark field, you know what is a dark field mask and a light field mask. With a negative photoresist, will cause the exposed areas to, so this question, both of these is similar, so that is why I have kept the same slide. Dissolve during development, stay after development, harden and get etched. So what
Answer
happens
B.
to it's B, stay
Answer
after
B.
development, because it's a negative photoresist. And so why we are considering a dark field mask, say for example, so let's consider the example that we have already discussed. So this is our final structure, so this is SU8 pillar, and we want to want SU8 to be present only at this portion. So the questions we are discussing, so this is are considering the example that we have already discussed, the fabrication steps we have already discussed. So we will use a dark field mask which will be mostly dark, and light will not pass through it. Light will pass through only at this portion, okay, where we want SU8, and it will become hard after exposure. Okay. So the type of the mask will depend on the final design we are expecting and the photoresist type we are using. Okay. Whether it's a positive photoresist or a negative photoresist. If it's a say, if instead of a negative photoresist we are using a positive photoresist, then it will be a bright field mask. So mostly we want that everything will go away. Okay. Stay after development. Next question. So this is more like a general question. You can try to answer, give few points. Okay, I have tried to keep some multiple choice, some true and false fill in the blanks type question, and few other short questions that will give you some opportunity to think, like instead of just giving you the options. Okay, so how can you detect and troubleshoot a vacuum leak in a PVD system? Suppose you are using a physical vapor deposition system, and there is some vacuum leak. Okay, so how can we detect that, and how can we find out where the leak is? Just think that you are working in a lab, and we are facing this problem, like it's a practical problem that we are facing, and we need to find out the solution. So how we will do that? So I will wait for some time. I want at least few answer from your side. What do you think? So you have gone through the lecture videos where different physical vapor depositions, the installation of the system was shown. So probably you'll be able to answer this.
Ma'am, a sound will come. A sound will come that will tell that there is a leakage by hearing a sound. That is one method without any instrument. And vacuum will never be complete. Means uh, it
It will
will
not
never.
reach to that value.
It will not reach up to a certain level that we want.
Yes.
And a sound will come, like hissing sound will come. So that is the indication without any instrument. And if we have instrument, then we can go for like solvent testing and other type of the testing.
Yes, whatever you have explained is correct. I think you might have some experience. So, how can we detect the sound that you mentioned? So, normally, usually the turbo pump or other pump that creates very high vacuum, they usually make some sound because it rotates, or like it accelerates and then at a very high speed. But otherwise, if we are say using a rotary pump for initial vacuum, and then initially when we start, if it's like a normal environment, then the pump sound will be very high. Okay, as the vacuum, like the pressure decreases, the pump sound also decreases. So we have to be always careful while working in the lab that whether the sounds are like usually we hear, or like something unusual is happening. Okay, if the rotary pump is making much like a very large, like the sound is more than usual, and the vacuum level is still not reaching, say using a rotary pump we expect say 10 to the power minus 3 m bar, at least minus 2 m bar, but it is say fluctuating between 0 and 10 to the power minus 1 m bar, then probably there is some leakage. And in that case we should not turn on the high vacuum pump, say turbo pump. Okay, if there is a leakage, first of all we want to save our pump that will create high vacuum. Okay, so first we will try to create vacuum using the rotary pump, and if there is some problem we have to stop it then and there. So for we have to short it out first. And how we can find like where is the leakage exactly? So I will what you have mentioned, like using some solvent, yeah, that is correct. Say we have a pipe and there is some like very small hole or something through which there is a leakage. Okay, how we can determine this? Say we somehow we know that there is a leakage, there may be a leakage in this pipe. So we will use some soap water solution. Okay, we'll make some soap water and we will spray some over here. Okay, if we will try to pass gas or something, then because of there will be soap water on top of the pipe, there will be bubble formation, and this bubble formation will increase over time. And like how rapidly the bubbles are forming and these things happening, that will tell us like how big our leakage is. Okay, so this is one test we often do. And another thing is that, as I mentioned, in a physical vapor deposition system, we will have a main chamber. There will be one door and we will close it. Okay, there will be other connections. So when we make vacuum, when we join any two components, there will be a rubber o-ring between the components. Okay, so there will be a o-ring. It may be like spherical size, it can be of a square size also. There is one rubber o-ring, there will be one rubber o-ring, the shape can vary. And if there is some cut in the o-ring, then also uh, the vacuum will not create. Okay, even though we'll try to close the door, we'll try to connect the components, and if the o-ring is not proper, there is some particles say on top of the o-ring. Okay, that is also might create leak. Okay, and then if there is a cut in the o-ring, so o-ring is like a rubber pipe kind of thing. Okay, that actually holds two components together and creates vacuum. Okay, many times the o-ring gets damaged and there will be a vacuum. Okay, these are the things we will check first if we sense some vacuum leakage in our system. So I will write everything so for your reference. So the indications will be slow pump down time, so it will take a lot of time, say, to create vacuum. Maybe it will be able to create some vacuum if the vacuum leak is not that significant. Okay, and there may be some pressure fluctuations. And if it's a big leak, then it will not be able to reach the base pressure. How we can detect it? As I mentioned, soap solution taste. Can be like inspection of common leakage. Mostly those are in o-rings. Sometimes they may not be arranged properly or sitting at the place where it is required properly. Okay, and flanges and seals. Okay. we have to check that these are properly aligned and properly tied and it's tight. Okay, flanges are like this kind of thing. So we will put something, and I don't know how to draw it. Maybe you can Google how this flanges and sills look in a PVD system. Okay, so these are like a circular kind of thing that we use to close something. We have to check these places first. If the leakage is not in some pipe or something, okay, we will check this, and we'll try to short it out first before doing any deposition, before turning on any pump that will create high vacuum. Okay, we don't want to damage our pump. So this is about PVD system. Let's go to the next question. In sputter deposition, which gas is commonly used to create plasma? The options are oxygen, B hydrogen, C argon, D nitrogen.
Answer is C, argon.
Answer is C argon. Okay. What about others? I'm getting answer from only few people. So in sputtering we use argon gas as the sputtering gas. Why use argon? So argon is an inert gas, so it will not react with our target material. Sometimes inside our sputtering system we will have multiple targets. We don't want any kind of contamination, and also the film we are depositing, the target we are using, we don't want any contamination there also. So that is why we use argon, because it's an inert gas. And what happens in sputtering, so how it happens, it's a PVD technique, physical vapor deposition technique. So argon ions will hit the target and will eject some material, some atoms from the target. Okay, the sputtering targets are usually like maybe 2 inch 4 inch diameter. So argon will hit the target and remove some material, some atoms from it. Now for this effective sputtering, effective removal of material, the atomic weight of the sputtering gas, that is argon, this should be similar to the atomic weight of the target material. That is why many times we use argon, but if it is a very light material, then we will use a different inert gas, and if it's a very dense material, the weight is very high, then we will use different material. But for most common sputtering targets, argon is a good choice. We can easily create plasma of argon and then do sputtering deposition. Okay, so I'll write it here also. To the next question. evaporation the source material is heated using either dash or n dash source. So I will not give you the options, you will be able to understand. So what are the types of evaporation? Either thermal evaporation or e-beam evaporation. So how we heat and melt the target material in different type of evaporation. So what are the techniques? So you can fill this blank, you can write these two words or set of words, okay, in the chat box. I will wait for something.
So, ma'am, one is filament, other is e-beam.
Yes, so it's a resistive element, we can say that, instead of a filament. So why I am saying resistive element? Because we use Joule heating. We apply a current to the resistive element, and because of Joule heating, heat is generated and that will melt the target material or the source material. Now this can be like we can use like a basket or like a filament. So this can have a spiral kind of structure. It's difficult to do. Okay, so there will be these two wire and we can place our metal here. So this is one configuration. This is usually not preferred. Basket is not preferred because our material will melt and go below also. Okay, so instead of that, what we use a boat. So this is a boat and this is a basket, and this is a resistive element. Okay, just simply saying it as a resistive element. We'll connect our electrodes here, we'll apply current through it. Now the boat will have a melting point that is much higher compared to the source material. Okay, we can have a boat of molybdenum, okay, tungsten also. Then these materials have very high melting point, if I think around 3500 degrees Celsius, okay, or Fahrenheit, I don't remember. You can check what is the melting point for molybdenum and tungsten. So we use a resistive element and we use electron beam in case of e-beam evaporation when the melting point of the material is very high. Okay, now in that case also we will use a crucible to hold our source material, but we will not apply our electron beam directly to the crucible. So the crucible can be of graphite, again that can sustain also high temperature. So we definitely need to use a material that can sustain high temperature, because these are high temperature processes. But we mainly use a focused electron beam to melt our source material. And how we can manage our electron beam? Okay, because it's a beam of electron, it can be deflected by using electromagnetic lens. We have discussed about what is an electromagnetic lens. Okay, basically electron can be deflected by using a magnetic field. Okay, electric field and magnetic field is correlated, that we know. Okay, so we can move electron beam, we can deflect electron beams using electromagnetic lenses, and by electromagnetic lenses I mean that we can create electric field, magnetic field, and that will deflect our electron beam to the desired portion of the source material. Okay, so normally what happens, If I show you the top view, so this is our graphite crucible, the outer portion, and we are keeping our target material here. So we'll try to focus our electron beam at the center, and we will move our electron beam like this. We don't want to hit our graphite crucible, and we'll try to keep our electron beam inside this source material. We will try to melt it evenly so that we get a like a very good deposition. So this is used for materials with high melting points, but for most metals, thermal evaporation using a resistive element is a very good option. Okay, it's a relatively lower cost system, thermal evaporation, compared to a EVM evaporator, because EVM evaporator requires some external like some other components, like to create the electron beam and to deflect the electron beam and all these things. Okay. Let's keep it. Next question. So this question, I have kept few questions on the CAD tool that was discussed in the lecture videos, Autodesk Inventors. I have not discussed much about that 3D printing technology and particularly the software. I hope that you have gone through the videos. This is just to like give you an example. Similar questions are included in the assignments or may come in the exam as well, so that is why I have included few questions on that topic. Which feature in Inventor allows a 2D profile or a 2D design to be turned into a 3D object? I'll give you the options: fillet, extrude, shell, loaf.
Answer B, extrude.
Extrude. Yes. So this is one feature. In the software, we can make a 2D design and convert it into a 3D, and the feature that is used is extrude. So basically it gives depth to our design, thickness to our design. There are similar softwares also where we can make this kind of design. I'm sure there will be some feature to make it from 2D to 3D. So I don't have many questions, so this is the last question. We still have time, so this is like an open-ended question. I will give you the question and maybe you can think and give me few answers, and this time I want answer from all the people present in the meet. Okay, so this question is a very general question. So we have discussed about 3D printing. Okay, and this is particularly very useful in the context of the score sensors and actuators. We can make different designs using this technology. So what do you think, what are the main advantages of 3D printing technology in sensors? Okay, so the question is, what are the Advantages of 3D printing in sensor technology. Maybe you can write a few in the chat box, then we will discuss.
It can create complex shape.
It can create complex shape, yes. So we can make the design using some tool, and we can just go for 3D printing. But what can be the other advantages, and what do you think that what are the disadvantages in case of 3D printing?
Strength is not too much, strength is less. And many times we cannot use same component as a structural component.
Yes. So we are limited with the material with which we are printing. So we have to make like a ink. So this is a printing technique, right? So to make the ink, so that is where the limitation is. We cannot use the same material for in all our design. Many of our sensor characteristics depends on the material properties, and if we cannot make that material, we cannot make ink of that material, we cannot go for 3D printing. Support wise, what you have mentioned, that yes, the actually that is again come from the material that we use for 3D printing. So those may not have very good mechanical strength. Okay, usually does not sustain very high temperature. So at least from what I have seen, that the materials cannot sustain very high temperature, like alone by itself. And but many people are working in 3D technologies. The main challenge is to make the material compatible to 3D printing. If we can make the ink of our material, of our desired material, with the properties of the material. Say we are designing a sensor, and we are using a simple sensing element, sensing material, and the properties of this sensing element or the sensing material will change. Say the resistance of the material will change due to some target analyte. Say we are using it as a gas sensor. I'm just giving you an example. If we can make like a ink of that material, of our desired material, we can just take some platform, some substrate, and then we can maybe do a 3D printing if like it bonds with our substrate, and then we can go for like 3D printing very easily. The problem is the ink that we are using for 3D printing. So many research groups are working in that, so that we can make material that is compatible for 3D printing. And if we can make that ink, we can make complicated structures also using this technology. So these are some advantages. I'll write it down for your reference. So first advantage is rapid prototyping, because this process is generally fast. We have to make the design, we can just go for printing. So you know that other microfabrication techniques involves a lot of steps. Even the photolithography involves multiple steps. Okay, it does not require all the steps. So rapid prototyping is definitely one advantage. So this leads to faster fabrication, testing, as well as implementation. Next is, as we have discussed, complex structures can be made easily. Now remember, because it's a 3D printing, so there will be like a nozzle through which this printing will happen. So it is not possible to make very fine structure. Okay. So that is one limitation. So obviously we cannot make like a very thin structure. But if it's a relatively larger dimension, then we even for complex structures also we can go for 3D printing. Third is, we can combine multiple materials to a make our structure, make our sensor. As desired. Okay. As I mentioned, many people are working in the ink for 3D printing. So how we can combine different materials to achieve different properties. Yeah. Next is, it is cost effective compared to other fabrication techniques because it does not require a lot of like machines. Okay. And we can do in a like a normal lab setup even if we don't have a very like sophisticated clean room. Now these are advantages when we think of like a low cost production and say large scale production. But if we want to make a very sophisticated device, very accurate, with great accuracy, great sensitivity, then this may not be a good option. For that, we still have to go for like MEMS based sensor with different like complex design and different microfabrication steps. Okay, but for low cost sensor, if we can make it using 3D printing, then we can easily go for commercialization without having like a lot of facility. And one more advantage is, so this is not directly an advantage, but I just want to include that it it does not involve a lot of material waste. Okay, we will make the design, we will print whatever we need. But in other cases, there like other fabrication techniques, there will be a lot of wastage of chemicals and other materials. We will do etching, we will use developer and other things. So in that way, it is kind of eco-friendly, and it eliminates any material waste. Okay, so these are some advantages of 3D printing. So I don't have any more question. If you have any doubt, you can ask. Okay, we still have some time, so if you have something, then you can ask. Okay, so these are from earlier. I hope that you are going through the assignments and submitting it on time, and Maybe some of you have registered for the exam, so the exam will be, I think, at the end of April. I hope that people who are present in the meet, they are actually listening to me and got what we have discussed. If you have any feedback, any suggestion, and any doubt, you can tell me.
Hello.
Yes.
Madam, in the last assignment, there is a question, assignment number 10. What is the reason for using PECVD for depositing silicon dioxide during the fabrication of piezoresistive microcantilever?
So we have discussed this
I
in today's class also. So the main advantage of PCVD is that the operating temperature is low. So that is
Yeah,
why.
madam. Actually, I clicked that option only, but they are in the answer. It is less time consuming process mentioned.
Okay,
Out of the
maybe
three
you
options, easy
can.
process. Yeah.
Okay, maybe you can raise that in the discussion forum. So
Okay, ma'am.
from my so what I think, so it is mainly because of like low temperature process. But if the question is specific to, let's say, some problems related to, then maybe the team that is handling the assignment question, they will be able to answer. But mostly we use PECVD because it's a low temperature process.
Okay,
And the
ma'am.
example that today we discussed, in that case specifically it is for low temperature because we are dealing with flexible substrates. Okay, flexible substrates usually cannot handle high temperature. So any other question? If not, then we will stop for today. We will meet in the next week, next Tuesday. Before that, I might take one doubt clearing session also, like that will be more like a summary session. It will be a short session where I will like discuss maybe the summary of the course. It is not sufficient to discuss like a 12-week course in a 1 or 2 hour. So but I will try to give you a summary and discuss maybe few questions. Okay. uh, you will be notified in due time for that. Now it depends, I might take or might not take, let's see. But we will anyway meet next Tuesday at the same time from 6 to 8 p.m. for regular live session. That will be for week 12. Okay. So if not, then there is no question or doubt, anything to add, then maybe you can leave. I will stop the session here. And thank you for attending the session. I hope that the session was useful and I delivered something that will be useful for your exam, for solving assignment, or useful in general. Okay.